So what I'm going to talk about today is, to what extent is population change a cause of some of these challenges, or perhaps it's actually a symptom? In order to do that, we need to talk about things like rates of change, but in a non-mathematical context, because again, referring back to the feedback, some of you have got quite strong opinions on maths. And as I said at the start of the course, there isn't any mathematical element in this module. We talk about things which you can describe in maths, but I'm not going to ask you to do anything mathematical. But I am going to ask you to think about population change and the other global challenges in terms of this thing called system dynamics. So I describe some of the concepts that we're going to need today. So this is the You're All Doomed module. Well, there's another context, there's another way of looking at it, and that's a much more optimistic way. Who's heard of Hans Rosling? Anyone? He's the kind of the joy of stats guy. He's done some documentaries for the BBC now. This should work. I'm going to show you the output of something called GAPMINDER. Anyone come across GAPMINDER before? All right, do you actually use it in some of your modules already? People teaching with GAPMINDER? I would have thought some people do. You might have already seen this one then. Even if you have, it's worth repeating because it is pretty cool. So what this shows is the last 200 years or so and the story of development. So on this axis here, you've got income per person. This is a logarithmic scale. I'll talk about that in a bit. But basically, this is people who are being very poor, and this is people becoming richer. And over on this axis, you've got life expectancy. That's not on a logarithmic scale, that's just linear. And it starts off in 1800, which I think you can all see. And all the countries in the world are in this corner here. People don't have an awful lot of money, and people don't live particularly long. Life expectancies around the middle 30s, maybe up into the 40s. The countries are color-coded. If I can just rescale this. Right, yeah. So the orange balls, they relate to countries in Europe and Eurasia. The blue, dark blue, is African countries. Light blue is mainly India. Red is the Southeast Asia, Australasia, and yellow the Americas. And the size of the ball relates to the size of the population. And there's a little key here. So when the ball is about this size, then it's 1.36 billion. Right, so we're going to start at the start of the 19th century. So you can see everybody's pretty much in this bottom left-hand corner, but you can see there's an awful lot of variability already in some of the orange circles. So these are the countries in Europe, and this is the process of industrialization. So people are becoming quite rapidly more wealthy, and their life expectancies change quite markedly. There was a big dip there. That was the First World War, the carnage of the trenches. We're going now to Second World War, post-Second World War, and you can see the trajectory is that pretty much all the countries are migrating up into the top right-hand corner until we get to today, where there's not a tremendous difference between the some of the countries in Asia, the red circles, and some of the countries in Europe. Here's the United States. This great big circle, unsurprisingly, is China and India. So the trajectory is that certainly China is catching up, and so is India, but there's this quite long tail. There's a long tail of countries which still have, relatively speaking, low life expectancy, and relatively speaking, not a great deal of money. Now, for some people, that's a cause for optimism, because it's telling us that in a mere 200 years, there have been tremendous changes in people's well-being in terms of how much money they've got, their quality of life, and how long they live for. So, the question is, and maybe I'd just like you to discuss this in pairs, just for a couple of minutes again, to what extent do you think there are limits to that trajectory? So in 200 years, most of the world's population, there's a significant bottom billion, mainly in countries in Africa, but most of the countries have undertaken this kind of rapid transition, this kind of rapid process of industrialization, and have moved over to the top right-hand corner. Are there any kind of limits to that trajectory? Can everybody get in that corner, and can that corner continue to extend further upwards and further to the right? So just a minute or two with your partner. I'd just be interested to have a chat to see if you think there are any limitations on our increase in the amount of wealth that we've got, and maybe even to the extent in which we can actually live longer lives. Okay, just a couple of minutes on that. Well? Hopefully that was productive, or at least interesting. Anyone heard of transhumanism? The transhumanist movement? Really? Well done, sir. Okay, so transhumanism is this idea that by using technology we can undertake kind of an artificial evolution of Homo sapiens. So in principle we could maybe live forever. You've all heard of the Cybermen, right? Doctor Who? Maybe that's one such reason why transhumanism is such a good idea. But you know, there are people who seriously consider it. Anyway, most people, I would think, would say there are certain limits. There are certainly energetic limits right now. Maybe there are other kind of limits. And to a certain extent, we're going to be talking about them in this module. And we're going to be talking about them sometimes in the context of sustainability, which gives me an opportunity to plug my latest module, or rather than program of study. Don't worry, 15 seconds. Sustainability Masters. Sustainability Masters. Currently developing a new master's program, a Master's of Science in Sustainability. It's very much the thing to do these days. Okay, so we're jumping on the bandwagon, of course. It's sort of a development of this module, but at a postgraduate level. Sustainability. Who's heard of XKCD? Randall Munro? Never mind. Right. Go to xkcd.com and look at all his other cartoons. He's a very funny chap. What this shows is the frequency of the word sustainable. Is it sustainable or sustainability? Yeah, sustainable since 1960. Okay, what about 1955 or so? Up to the present day, and then extrapolated at some point into the future. Okay, and here's the frequency of the word sustainable used in English text as a percentage of words by year. So back in 1955 or something, 0.000001%, you know, nobody was really using the word sustainable in English text. But as you go forward, as you regress a line, as you put a straight line through all these different data points, you get to today where it's an appreciable fraction, 0.01%. Now, if you continue that trend, so in terms of regressing the data, which some of you might have done, you carry on that straight line here, then by 2036, at this rate of change, the word sustainable will occur on average, once on every page of English text written. Until 2061, sustainable occurs on average once per sentence. And if we were to carry on this trend, by 2109, everything that is ever said in the English language is just the word sustainable repeated again and again and again. So hence the caption, the word sustainable is unsustainable. Its rate of change cannot be sustained. Now, this kind of sums up part of the bandwagon that's being jumped on in terms of producing a new sustainability masters, but it also demonstrates something called exponential growth. So when you see a figure like this, where you've got this linear axis, these are going up in regular increments, 1960, 70, 80, 90, 2000. But these distances here are not the same. These are going up by factors of 10. This value is 10 times more than this value. This value is 10 times more than this. So 0.1, 1%, 10%, 100%. Whenever you see a straight line here with this logarithmic axis, it's telling you something, and what you're looking at is an exponential function. There's an exponential increase in the use of the word sustainable. So this is pretty much the only maths there is in the module, I think. I was looking through the slides the other day. I thought, am I going to put in a function or two? I thought, go on, why not? It's at the start. They can take it, can't they? So I'm showing you a couple of, well, 3 mathematical functions. Anyone read, well, in case there are some people who are red-green colorblind, a significant fraction of the population, one of my pet peeves is that for some people they can't really tell the difference between those 2 lines. People are always doing this all the time. They need to at least label the function. So this is the output of function A is this one, B is this one, and C is that one. Anyway, the point I'm showing these is that the function A here, that is a linear function. It's a simple, steady rate of change. So basically, whatever the value of x is here, then the value of y will be 50 times that. So when x is 1, y is 50. When x is 10, y is 500. The blue, or number b function, that's not a linear one. That's nonlinear. It's a cubic. Basically, it means take whatever the value of x is and times it 3 times. So if x is 3, then times 3 by itself 3 times, that's 3 times 3 times 3 is 9, is 27. So it's 27 here. When x is 10, so that's 10 times 10 times 10 is 1,000. So then that means it's that value there. But this is the interesting one, right? This is the exponential function. And what the characteristics of exponential functions are, with low values of x, they don't really do a great deal. Because they're called exponential functions, because this term here is called the exponent, and you put the value of x in there. So this is saying when x is 2, then 2 to the power of 2 is 2 times 2 is 4. When x is 3, then that's 2 times 2 times 2, that's 2, 4, 8. So these are very, very small values, but you can see it kind of takes off quite suddenly, and that's the characteristic with exponential functions. They start off with relatively small numbers, but because they're continually doubling, and the rate of doubling or the rate of increase is a function of how much of it there are, they can undertake quite rapid growth. So there's kind of a hoary old example which has got to do with rice or wheat and a chessboard. Who's heard of this one? Anyone? Excellent. Right, so the story goes that back in, and it depends on which country you want to tell it in, but let's say it's based in India, you know, a few hundred years ago or something. There was a wise mathematician who solved some problem for some king or sultan or something, and the king or whatever sultan said, well, as a reward, you can name your price. So what do you want as a reward? And so this mathematician, knowing all about exponential functions, being a very clever mathematician, told the king, my needs are humble. All I want is a single grain of rice on the first square. But then on the next grain of rice, I would like double the number of grains of rice. And the next square, I'd like double of that. And the next square, I'd double of that, etc., etc. So what that means is you start off with 1 grain of rice, then 2, 4, 8, 16. And the king or sultan or whatnot said, after a few seconds of reflection, most probably, well, yeah, like a few grains of rice. We have, you know, hundreds or thousands of bushels of rice or sacks of rice in the stores. Perhaps the mathematician isn't so clever after all. Or maybe he's just a bit idiosyncratic. However, what the king didn't realize, if you keep on this process of doubling, you're going to produce some quite literally astronomical numbers. So the number of rice on the very last square would be 2 to the power of x, so that exponential function, because we're just doubling it every time. And x in this instance is 63. There are 63 squares prior to that. So if you want to know how much rice is on the total chessboard, then the total is 2 to the power of 64 minus 1. How much is that? That's 18 million grains of rice. Or to put it in scientific notation, 1.8 times 10 to the power of 19. It's a gargantuan number. It's absolutely huge. If you assume that each grain of rice is about 20 milligrams, I suppose, then if you could get that amount of rice, and you can't because it's many thousands of times greater than even today's current rice production, then the mass of all that rice would be significantly greater than the mass of Mount Everest. It's an astronomical number. Now, people sometimes, you may have heard the expression, the second half of the chessboard, okay? What that refers to is there are kind of 2 problem domains. So this is the chessboard. This is a representation of that problem that we just had. So you start off with a single piece of rice. Then you do 2, 4, 8, 16, 32, 64, 128, 266, 512, 1024, 5, you know. And you can see that obviously you're starting at very small numbers. But this side of the chessboard, okay, you end up in 2G, so these are billions. So these are 2 billions. So these are large numbers, but you know, they're not astronomically large. But if you look where we go very, very rapidly in the second half of the chessboard, you end up at exobytes, you know, to the powers of 19, to the absolutely gargantuan, the impossible to realize numbers. And so sometimes you might hear that. We have a problem which is either in the first or in the second half of the chessboard. We don't want to get the problem space in the second half, because if you do, it'll be impossible to control. Some people, for quite a significant period of time, well, a few decades at least, were worried that global population was moving into that second part of the chessboard. So this shows population, human population, back to about 1 million years ago. So here we are today, back 1 million years, and these are the global population in billions. So we've got the old Stone Age, Bronze Age, etc. And you can see for most of human history, the total numbers of humans across the entire globe are in the orders of millions or tens of millions. A couple of hundred years ago, about 300 years ago, we started moving into hundreds of millions. And then around the 19th century, the start of 1800s, something quite remarkable happens. The population just explodes. It undertakes this exponential growth. So if Homo sapiens, humans, have been on the Earth for about a million years, it took pretty much almost a million years for us to reach our first billion. Then it took 123 years for our second billion. But then you can see the time between the increases in the numbers of billions of global population was getting very, very small. In fact, between 1974 and 87, it's like 13 years. Now, who's heard of Thomas Malthus? Everyone's heard of Thomas Malthus. Cheery, chappy Thomas. Right. So Thomas was alive in the 18th century. He was alive when, and he witnessed firsthand the tremendous increases in some of the cities, and the size of London, populations and other areas in the world. And Malthus is a controversial figure for some, I suppose, but he had a very, very important observation. His observation was, if you're considering how you can change, or the rate of change of the amount of food that could be produced for human consumption, then you'll be looking at either this kind of red line, remember this linear function, or maybe a non-linear, this cubic function, this blue one, right? If you're optimistic, you could imagine that this might go up a bit steeper, this blue one. But there are only so many improvements, so he thought, in terms of animal husbandry, the ability to rotate crops. He imagined it as technological limitations, maybe even societal limitations. How fast, how quickly can you grow food? How efficiently can you grow food? And so he imagined, you can be optimistic if you like. But one thing you'll never be able to outrun is something which increases exponentially. And he was characterizing the change in human population as an exponential function. And for a while, certainly he was right. It was increasing. These periodic doublings of population were coming down to a matter of decades. I mean, the world's population is now a little over 7 billion, and that's doubled in the last 45 years or so, maybe a bit more than 45. So whilst these functions may be able to keep pace with your increase in population, wait long enough and there'll be a sudden increase. And when there's a gap, either a gap between this red function or this blue function, the thing that's going to fill that gap is starvation, malnutrition, and ultimately death, by which then the population will come back down. So I'm going to talk about population, but I want to talk about it just like I want to talk about all the global challenges, not necessarily as a demographics issue, but as an issue to do with system dynamics, a way of thinking about rates of change of population. So, in any kind of system, you've got elements, bits, entities, agents, individuals, and they interact. They have some kind of effect on each other. So in a population system dynamics context, what you've got is a population here, and you've got things coming in, babies, and you've got things going out, corpses, ignoring any kind of migration. So the reason the total number of people are changing is because numbers of babies are being born might change, and numbers of people that are dying might change. And so you can look at them as flows, kind of like flows which are being modulated or adjusted by taps. So there's a flow in, and then there's a flow out. And all this is saying that there are just some specific system dynamics terminology that we can use to describe that. So the thing that we're interested in, which is the population, which is we can call a stock. And a stock is just the thing that we're interested in. It could be people, it could be energy, it could be information. You have a source, where stuff comes into that stock, and you've got a sink where stuff goes to out of that stock. And you've got flows. You may have flows coming in and flows going out. And in principle, that's generalizable to a very wide range of issues. It's certainly generalizable to lots of the global challenges that we're going to talk about. So that's in terms of population. But to talk about flows and stocks and sinks more explicitly, we can talk about baths. Right, so imagine that you have a bath and water flows in via a tap. Now, one of the reasons we call that a source, we kind of put a cloud around it, is because we're not particularly interested where it comes from. I mean, when you turn the tap on in your bath or shower, I guess you think it comes from, I don't know, like a reservoir or something, or it comes down from rain. But for the purpose of this system, we're not really interested in where it comes from, and we're also not particularly interested where it ends up, which is some kind of wastewater treatment. All we care about is the level of water in the bath, let's say. So we can say that the amount of water in the bath is some kind of function or is some kind of consequence of what the tap is doing and what the plug is doing. So assume that the plug is in and the tap is open, then the water level is going to go up. Things begin to get a bit tricky because we can also imagine that what the tap is doing is in some sense dependent on what the water is doing. So in a human context, that's pretty easy to understand because you open the tap fully when there's not a lot of water in the bath, and as the water level comes up, then you start to turn the tap down and you close it right at the point where you want that water to be. What this means, and it doesn't matter if you don't understand this, but for those of you who do, it might help situate a bit of what we're talking about. We've got a pair of differential equations. All this means is that the change in water over time is dependent on what the tap is doing. So if I have the tap on full, then there's going to be a large change in the water. But then also the change in what the tap is doing over time is dependent on what the water's doing. A affects B, but then B is affecting A. Hey, who's doing zoology or biology? Anyone? Right, so predator-prey dynamics, Locked-Volterra systems, these are classic systems where the total numbers of predators, so imagine these are foxes, is dependent on the total number of prey that they can eat, so these might be rabbits. So as the numbers of rabbits go up, they can sustain high populations of foxes, but then the foxes get so abundant they actually lead to a population collapse in the number of rabbits. So then that means there's a collapse in the fox population, at which point then the prey species can recover, but then you see the same cycle again. So you get these very complicated dynamics, kind of boom and bust, because these are coupled systems which are interacting with each other. We'll consider something a bit more simple. So basically, the tap is dependent on what we're doing with the water. So let's make a really simple kind of function, a kind of a simple rule by which we open and close the tap. Let's say that the more water there is in the bath, then we should open the tap more. So what that means is the water level goes up, we open the tap more. The water level goes up, which you open the tap even more. So we're going to flood the bath, which seems a very silly thing to do. That's an example of this kind of system where, as the water increases, has an increasing effect on the tap flow, and as the tap flow increases, has an increasing effect on the amount of water in the bath. So that's an example of a positive feedback loop, sometimes called reinforcing feedback or runaway feedback. As A gets bigger, it makes B bigger, and as B gets bigger, it makes A bigger, and it goes on and on and on, faster and faster, or quicker, or higher, or larger, or however you want to measure the system. And that ends typically in two ways. The system overshoots and collapses, so you can imagine the bath overflows. Oops. Or something comes along and stabilizes that system, typically through what we want to call a negative feedback loop. So negative feedback or stabilizing feedback or balancing feedback, in which now if B increases, well that has an increasing effect on A, so that A goes up. But then as A goes up, it has a decreasing effect on B, so B goes down. So what negative feedback loops tend to do is stabilize perturbations. So if I start to try and move B around, you'll see a commensurate change in A so that B moves back to what its previous state or value was. What does that mean in the context of population? Well, this is our stock. This is stock of people. And this is our flow in. This is our births. Now imagine the birth rate is fixed, so there isn't any change in the birth rate. The average number of children that people are having per capita, per couple, is fixed. And you can see that as the population goes up, then that's going to produce more births. And then more births means that the population is going to go up. So you can see there's a possible positive feedback loop here, all things being equal. But over here we have a kind of stabilizing loop, because the greater the population, the greater the number of deaths, with, again, a fixed death rate, so that will lead to a reduction in the population. So you have a stable population when these kind of two components, these two loops or subsystems, are equal. So when the birth rate is equal to the death rate, then we shouldn't imagine much change in the population. If the death rate goes up, then we should expect the population, the amount of stock to go down. And similarly, when the birth rate goes up, then we expect the population to go up. So it's the balance of these two processes, death rate and birth rate, which is the kind of foundation of this thing called the demographic transition. So who's doing demography? Who are the demographers? You're identifying her for me, thank you. Right. So who's heard of the demographic transition? Oh, super. Right. So you all know what the demographic transition is. So in stage 1, we typically have here. This is the death rate, and this is the birth rate. So we typically have quite high birth rates, but then you also have high death rates. So it doesn't matter what the absolute values are, 1, 10, a million. All that matters is that they're the same, or approximately the same value. So they kind of balance each other out. And they go up and down a bit, and you'll see natural increases or natural decreases. What happens here is this interesting process where there's a significant and sustained decrease in the death rate, and then later on, there's a commensurate decrease in the birth rate. And the difference between these two decreases is what produces that increase in population. And because once you start with an increasing population, all things equal, you're setting the system up for exponential growth, you can see quite sudden and dramatic changes. So this is just an example of a model output of a demographic model where you can see there is a birth rate here, there's a death rate which undergoes significant declines and then reflexes back here, and then that's kind of caught up later on by the birth rate, with the total population undergoing this sharp increase here but then stabilising off there. Right. Now, I want to go back to GAPMINDER because I think it makes the point quite nicely. If we look here, right, so we're back at the start of the 19th century, so this is back in 1800s. This is the same, this is income per person, so that's the same axis, but now this one has changed. This is now children per woman, so this is your kind of fertility rate, your total fertility rate. So once again, that's on a logarithmic axis, so the difference between these points isn't the same. You know, people are becoming much, much richer as you're moving over to this side. But this is a linear scale, so these are just differences in 0.5s, 2, 2.5, 3. So we start the 19th century, and again, everyone is kind of clustered around. You can see that the European countries are slightly lower and slightly to the right. So if we start that, you see once again that there's a kind of movement down and to the right. There goes the First World War again. Significant impacts on fertility then. You can see China is bouncing all over the place. Great leap forward, you know, long marches, things like this. But as we're moving towards the end of the 20th century and to the current day, you can see now there is, you know, in terms of income per person, we're quite spread out on this line, but we are very nicely clustered in terms of fertility, in terms of numbers of children per women. But again, there's quite a long tail. And this long tail extends all the way up here, all the way up to, you know, over 7.5 are for certain countries in Africa. So, in the context of global population change, we started at the start of the 19th century. This goes back a little bit. So this is kind of a zooming in on that global population figure that I showed earlier. And this projects up to 2050, but this is where we are today, 2015. And we can see the population's undergone this significant increase here, and there's been this massive change in the population increment, which you can see peaked. It peaked around 1990s, and has since then actually been coming down. It's projected to come down quite significantly. When I was born, which is hard to believe because I don't look as old enough to have been born in the early 1970s, but when I was born, in a period in history which saw the greatest rate of increase in global population ever in all of history, and most probably ever will, if we're right. If we're right, then this, and it's demographers argue, and we'll discuss this at length, but if we continue on this trend, then sometime by the middle of this century, sometimes by the end of this century, we could, at a global population point of view, come back down to effectively no change in the population. So globally, death rates will be balanced by birth rates. And the reason we're not there yet is because there's significant regional differences. So here we are in the United Kingdom, and for most of, or pretty much all of Europe, apart from maybe, Ireland, we live in low fertility countries. So for many countries in Europe, well, at least a few, and particularly a country such as Japan, the fertility rate is actually below the replacement rate. We're undertaking net decrease in population, ignoring in and out migration. Okay, so there's been a transition from high birth rates, high death rates, to certainly in some countries very low birth rates and very low death rates. But you can see the big red chunk of change are these countries in Africa, which some of them are seeing tremendously high still birth rates. So if you're talking to an optimist, the optimist will say, well, look, the problem is, if we want to stabilize global population, we need to undertake as much development, sustainable development, but we need to undertake as much development as we can of these countries in red. When we do that, their birth rates will naturally come down. So that's access to education and contraception, as well as maybe political, social reforms and increased wealth. So it's a kind of a natural, perhaps organic process by which we can control global population, at least get a handle on some of the large increases in population. So in that respect, they say, Malthus, no, he wasn't wrong, but Malthus and also the neo-Malthusianisms, some of which we will discuss later on in the module. In fact, I think one of the readings is from one of those thinkers, would say, okay, so in the developed world, we've got a handle on population, but that doesn't mean we've actually dodged a bullet. We haven't gotten over the problems of non-sustainable global populations. Because, going back to that thing I referred to in lecture 1, the perfect storm, it's still going to be the case by the middle of this century, we're going to have to produce at least 50% more food, access to 50% more energy, and access to at least 50% more fresh water, all at the same time as reducing all those impacts that you read about in terms of the planetary boundaries context. So even if you could stabilize global population, let's say we can stabilize it at 10 billion or 11 billion, we've still got to somehow drag all those people through a kind of eye of a storm by the middle of this century, not trash the climate, not consume all our finite resources, not completely exterminate most of the biosphere. And what this actually hinges around, I think what people are often alluding to, is they're talking about the global population or population change in terms of this thing that we might want to call total impacts. So I've got impacts here, total impacts. What's total impacts? Well, this could be total environmental impacts that humans have on the Earth. So you can think about it in terms of your ecological footprint. You've most probably heard the phrase or expression that if everybody lived like we in Europe or the United States live, we'd need about 2.5 or 3 Earths. The amount of resources that we require. So you can imagine, let's say by 2050, we'll have a global population of something, and then the total impacts, the total ecological impacts we're going to have is simply the total population times whatever the per capita impacts are. So impacts per capita, impacts per person. So when people are talking about population, they'll say they're often motivated because they want to reduce this number here. They want to make sure that the increase in this number is not so large that it means that this number becomes unsustainable, depending on where you want to put your level of sustainability or unsustainability. But really, that's not what they're talking about. The population change that we've got coming, well, most of the population change has happened. Population has doubled in my lifetime pretty much, and we're going to see another 3 billion or so. It's not so much that they're worried about, it's this. Because there's a bottom billion of people who still don't have a great deal. You know, those countries in Africa, maybe certain countries in South America or Southeast Asia. It's the change in this because they effectively want what we've got. So we have a billion, maybe a billion or two people who are becoming wealthier. They want to consume more meat. They want to consume more energy. They want what we've got. They want a television, a refrigerator. They want to fly on holiday. They want energy-intensive lifestyles. If we have 9, 10, 11 billion people with impacts per capita somewhat approximating ours, then there's no way that I can imagine, or anybody else, how we're going to keep the total impacts to within any notion of a planetary boundary. I don't think you'll find anybody who would sensibly argue that's the case. So the question is, how do we make room to allow people who have the very least in the world to increase their well-being, to be able to consume more of the Earth's resources, at the same time as there being a total increase in population, whilst not somehow going into an overshoot mode and collapsing very planetary systems that we depend on. So some of this I want you to think about in the context of the reading for tomorrow. So, Paul Ehrlich. Some people have heard of Paul Ehrlich, right? The Population Bomb. A very, very important book, published in I think it was the mid, maybe late 1960s, where Ehrlich argued that we are sitting on a bomb. So, you know, back in 1960s, the world's population was, you know, maybe just over 3 billion, a bit under. But he could see those rates of change. And he wrote this quite sensationalist book saying that if we don't get a handle on this rate of change, then it's going to imperil the very systems, the very planetary systems that we require on. And it's important to note, and in the reading that I've got for you tomorrow, he actually makes it clear it's not just the total numbers of people, it's the fact that there are more and more people who have very, very little, and if they have, or if they aspire to have the kind of energy-intensive lifestyles, the resource-intensive lifestyles that we have, then it's very hard to imagine how we cannot avoid collapse. So really Paul's got the darkest, bleakest interpretation. Paul is still, he's an emeritus professor, and we follow each other on Twitter. And the thing with Paul's tweets is everything is in capital letters with lots of exclamation marks, climate, calamity, disruption, disaster. It's pretty sobering. You're going to wake up on a Monday morning and you see what he's been up to, prophesizing the collapse of the world again. So that's kind of one extreme. He kind of encapsulates the neo-Malthusian point of view that we are fundamentally undertaking unsustainable population growth. The other thing I want you to do, now this is a video lecture, but it's not long. It's only 30 minutes, okay? And it's from Jane. So Jane Falkingham's the Dean of Social Sciences, so she's my boss's boss. And this is a video that I filmed with Jane last year, and she talks about Malthus, she talks about Ehrlich, but she also talks about alternative voices in geography, some of which you most probably already heard of. She gives a less pessimistic interpretation of where we might be ending up in terms of global population. So that's read that, watch that. Also, as an additional, and then this is Hans's, anyone seen this? Don't Panic? It was on BBC actually. It's about an hour long though, right? If you don't want to watch the whole hour, just watch the last 10 minutes, because he sets up your expectation that things are much, much worse than they are. And he does a very, very good job at that. But right at the end, when he talks about where we may end up in a kind of sustainable planet, he opens the box, or at least invites the discussion, well, obviously, we can't all have the same energy-intensive lifestyles that we have. So how are we going to fix that? So he kind of says, don't panic in terms of population change, but it leaves the question of those total impacts completely up in the air. So it's a very, very important question. Your additional task is find a toilet, take the little fit, and then flush it. Because what I want you to do, this is a siphon toilet, yours might look a little bit different, is see what's going on in this area here. So this is a classic example of a negative feedback loop system. Try and draw it maybe in a system dynamics context. Try and understand how it works. And finally, sorry, last thing, some of the feedback that I've been getting, people have been asking me about reading material, etc. It's already there. If you go to the website, look in resources, and there are separate tabs for the different global challenges. So you can thinking about that for your assessments. And also, the Assessment 1 template is actually online, and I'll be talking about the assessment a little bit more in the seminar tomorrow. Thank you very much.